Tonight, a quiet contradiction hangs over your head, and we're going to spend the next 2 hours sitting with it slowly, the way you might sit with a question that doesn't need to be solved quickly. The universe holds more stars than any single mind could ever hold. They scatter through space in every conceivable direction, and yet, most of what greets your eyes when you look up at night is darkness. By simple geometry, every line of sight through an endless field of stars should eventually land on the surface of one. The night sky, by that logic, should blaze as brightly as the sun, in every direction, all at once. Instead, the dark wins. The stars are the exceptions, scattered like rare sparks across an overwhelming black. Tonight we follow that contradiction all the way down through the air above your head, through the way cameras choose what to show you, through the way light ages as it crosses unthinkable distances, through the discovery that the universe itself had a beginning, and through the wider light our eyes were simply never built to perceive. None of this needs holding on to. Let your shoulders soften, let your breathing slow, let the day quietly drain out of you. Let's begin. On any clear night, away from artificial light, the sky offers a small, quiet puzzle. Your eye finds a modest number of stars scattered across an enormous field of black. Most of what's visible overhead isn't light at all. It's darkness, the space between the stars, the gaps between constellations, the long empty stretches where nothing seems to be happening. And yet the universe is vast beyond comprehension. It holds more stars than any number can make intuitive, more galaxies than imagination can comfortably survey. Estimates run into the hundreds of billions of trillions, and even that count only covers the portion of the cosmos whose light has had time to reach us. The true extent may be larger still, possibly without any limit at all. If there really are that many stars, and if every direction we could possibly look points eventually toward some galaxy somewhere in the depths, then simple geometry suggests every line of sight should eventually meet the surface of a star. The night sky shouldn't be dark. It should be uniformly bright as the surface of the sun, in every direction simultaneously. This is the puzzle we're going to sit with tonight. It's one of the gentlest, oldest mysteries in astronomy, and it quietly underlies almost every other question we ask about the universe. Not what's hiding in the dark, but why the dark is even there at all. For most of the history of curious thought, this question seemed to carry one obvious answer, and that answer turned out to be wrong. Resolving it properly required completely reimagining what the universe actually is and how it changes over time. It required discovering that the universe had a beginning, that space itself stretches as time passes, and that light from the most distant places has been traveling through that stretching for so long that it's been pulled entirely out of the narrow band our eyes evolved to detect. The dark sky, in the end, isn't an absence, it's a record. Tonight we'll read it slowly, page by page. Start with the simplest observation available to anyone. Step outside on a clear night, away from city lights, and look up. The stars scatter across the dome of the sky in their familiar patterns, bright ones and faint ones, single stars and loose clusters, smudges of light that resolve into many more stars under careful attention. There's the soft band of the Milky Way, which from a genuinely dark sight reveals itself as a vast, structured glow, rather than the empty stripe it appears to be from a lit city. There are perhaps a few thousand stars visible to the naked eye, though even careful counts vary, depending on conditions and individual eyesight. And between all of them, almost everywhere the eye lands, there's black. The black occupies far more of the sky than the lit stars do. This isn't a minor detail. The black is the dominant feature of the night sky. The stars are the exceptions. A photograph exposed long enough to fully reveal the stars will, in most directions, still show the regions between them staying dark, even as the exposure increases further. The night sky, to a close first approximation, is dark with a light sprinkling of stars, not the other way around. And this is precisely what raises the question. Consider what it would mean for the universe to be uniformly filled with stars, extending in every direction, going on without any end. A line drawn outward from your eye, in any chosen direction, would eventually intersect a star somewhere. If you look far enough through any small patch of sky, that line of sight, extended across cosmic distance, would have to encounter the surface of some sun, eventually. There would be no direction in which an infinite stellar universe could leave the line of sight permanently empty. Every line must terminate, sooner or later, on a star. If that were genuinely true, the sky wouldn't have dark patches at all. Every direction would terminate in starlight, and the eye, receiving that starlight from every direction simultaneously, would perceive the night sky as a continuous glow, roughly the same brightness as the surface of an average star. The night sky would be about as bright as the daytime side of the sun, in every direction at once. There would be no real night. We don't see such a sky. The night sky is dark. The stars stand out as lit points against a background that, to our eyes, holds almost no light at all. Something in this setup has to be wrong. The universe cannot be exactly the way that simple picture imagines it. Some assumption buried in the chain of reasoning, something that feels obvious or entirely natural, must be quietly mistaken. To find the error, we have to take the chain apart, link by link. We have to ask what we're really assuming when we say the universe is full of stars in every direction. We have to ask what it means for a line of sight to extend forever. We have to ask whether stars are eternal, whether space is eternal, whether light moves the way we instinctively think it does. Each of these questions, taken seriously, leads somewhere different from where we started, and the combination of all those answers gives us the dark sky we actually see. But before we follow those questions outward into the cosmos, it helps to understand the sky we see by day. The contrast between day and night is itself worth real attention. The daytime sky is bright, the nighttime sky is dark. The reasons behind this everyday alternation are part of the answer to our larger question, and they involve nothing more exotic than the air directly above your head. The first piece of the puzzle sits here in the atmosphere surrounding the Earth. Before we head toward the edge of the observable universe, we need to spend a little time in the air. It's worth pausing on the strangeness of the question itself for a moment. The dark night sky is one of the most common experiences any human being can have. Anyone who has ever spent a night outdoors, away from city lights, has seen it. For most of human history, this dark sky with its scattered stars was simply the universal backdrop of nighttime existence. Children grew up looking at it, travelers navigated by it, astronomers catalogued its features, poets wrote about it, and yet, for almost all of that long stretch of time, no one quite saw the dark sky as something requiring explanation. The dark was just the dark. The stars were the things worth noticing. The space between them was, if anything, simply where there happened to be no stars. It took a particular kind of careful thinking to notice that the dark itself was strange. That thinking required taking seriously the idea that the universe is full of stars in every direction, working out what that would logically imply, and then comparing the implication against what we actually observe. The implication is a bright sky. We see a dark sky. Once noticed, the mismatch refuses to quietly go away. It points towards something genuinely deep about how the universe is arranged. This is part of what makes the dark sky question so rewarding to sit with. It's built entirely from ordinary materials. There's no need for special equipment, no need for unusual locations, no need for advanced mathematics in the initial framing. Anyone who has counted stars and noticed the gaps between them already has everything needed to pose the question. The question itself marks the genuine starting point of cosmology. An enormous amount of further investigation follows from it, but it can be asked by absolutely anyone, at any time, simply by looking up. The familiar rhythm of day and night arises because the Earth rotates. One side of the planet faces the sun, and on that side the day is bright. The other side faces away, and there the night falls dark. This much is obvious, but it doesn't finish the explanation. It doesn't tell us why the daytime side is bright everywhere, not merely in the small patch of sky where the sun itself sits. If sunlight were simply a beam, it would illuminate only what it directly struck. Shadows would carry hard, sharply defined edges. The rest of the sky would stay dark. We'd see the sun as a bright disk surrounded by black, even at high noon. The sky around the sun would be just as dark as the midnight sky, only with a single bright point sitting in it. That isn't what we actually see. The daytime sky is uniformly bright, even far from the sun's position, even directly opposite to where the sun sits. The sky still glows blue. The brightness fills the entire dome of the heavens. The sun, though responsible for that brightness, is only a small piece of the overall picture. The rest of the bright sky is something else entirely, something the sun creates indirectly. To understand what daytime is doing differently from nighttime, we have to look at what the atmosphere does to sunlight. This turns out to matter in a way that extends far beyond our own planet. The same principle that lights the sky over a meadow at noon also explains why the moon's daytime sky stays black, why Mars's daytime sky glows pale orange, and why Venus's daytime sky takes on a sullen golden color with no visible sun at all. Each of these worlds receives the same sunlight. They differ entirely in what their atmospheres do with that light once it arrives. And that difference is the same difference that turns our own blue day into the dark night sky we're puzzling over right now. To understand the dark sky of the universe, we first need to understand the bright sky of Earth. And to understand that, we have to look closely at the air. Earth's atmosphere is a layer of gas surrounding the planet. From the ground, it doesn't look like much. It just looks like air. But this air, taken collectively, performs remarkable work on the sunlight pouring into it. When sunlight enters the atmosphere from above, it doesn't simply pass through and continue undisturbed toward the ground. It interacts with gas molecules along its path. Most of these interactions are gentle. The light deflects slightly, changes direction by a small angle, and continues. Some photons are absorbed and re-emitted. Some are simply scattered, sent off in a new direction, without any change in wavelength. The most important of these interactions is the scattering of light by gas molecules. Each air molecule is small compared to the wavelength of visible light. When a photon passes near such a molecule, the electrons within it oscillate in response to the photon's electric field, and that oscillation re-radiates the energy as a new photon traveling in a new direction. The probability of this happening depends very strongly on the original light's wavelength. Shorter wavelengths, toward the blue end of the spectrum, scatter far more strongly than longer wavelengths, toward the red end. The strength of scattering varies as roughly the inverse fourth power of wavelength, meaning blue light scatters roughly 10 times more strongly than red light through the same parcel of air. The cumulative result of all this scattering is that sunlight entering the atmosphere gets constantly redirected. A photon initially heading straight down through the air will, with some small probability, deflect sideways. That deflected photon may then encounter another molecule and deflect again. Over the full length of an atmospheric column, even a tiny per-molecule chance becomes a near certainty. The blue light, scattered most strongly, gets thrown around the atmosphere many times before finally reaching the ground or escaping back into space. The red light, scattered weakly, mostly continues along its original path. This is why the daytime sky is blue. Whenever you look up at any patch of sky during the day, in any direction other than directly at the sun, you're seeing sunlight that has been scattered by air molecules along that particular line of sight. The light reaches your eye not directly from the sun, but from every point along the column of air overhead, because at every point in that column, some molecule has redirected a fraction of the original solar beam downward toward you. The sky appears bright because it's genuinely full of redirected sunlight. It appears blue because the redirected light skews preferentially toward the blue portion of the spectrum. This same principle explains why sunsets turn red. When the sun sits low on the horizon, its light must pass through far more atmosphere on its way to your eye than it does at noon. The path length through air at sunset can run 20 or 30 times longer than the path at noon. Across that long path, almost all the blue light gets scattered away. Only the longer wavelengths come through largely undeflected, so the sun, viewed at sunset, appears orange or red because the blue has already been stripped from the direct beam before it ever reaches you. The sky immediately surrounding the setting sun takes on similar colors, sometimes deepening into rich oranges and reds as the path length increases further. The same atmospheric layer that scatters blue light during the day continues scattering it at night, too, but at night, there's no sunlight pouring into the atmosphere for it to scatter at all. The molecules are still there. Their scattering properties are still there. What's changed is the source. With no sun illuminating the air has nothing left to redirect. It becomes effectively transparent to the eye. The only light reaching you from any given direction is whatever happens to be coming from beyond the atmosphere along that exact line of sight. From most directions, that's the dim light of distant stars, or the even dimmer glow of more diffuse sources. From a handful of specific directions, that's the moon, a planet, or a particularly bright nearby star. The dark sky of night is simply what you see when the atmospheric scattering reservoir runs empty, so the brightness of the daytime sky depends entirely on having an atmosphere thick enough to do the scattering. Take that atmosphere away, and even the daytime sky goes dark. This is exactly what happens on the moon. The moon has almost no atmosphere whatsoever, only a thin exosphere of stray atoms, far too rarefied to scatter light meaningfully. The sky overhead on the moon, both by day and night, is the same uniform black. When the sun is up on the moon, the lunar surface is brilliantly lit. The rocks reflect sunlight directly. The dust scatters sunlight particle to particle along the ground. An observer standing in lunar daytime would see a bright lit surface stretching out around them. But the sky overhead would remain just as black. There's no air to scatter sunlight sideways into the line of sight, so the sky simply reveals whatever lies behind it, and what lies behind it is the same near-empty space that fills the sky at night. Day on the moon is a black sky over a white floor. The contrast is genuinely strange to imagine. On Earth, when we step into shade on a sunny day, we are still surrounded by plenty of light. The shade is dimmer than the sunlit ground beside it, but it's far from dark. Light reaches the shaded area from every direction of the sky. Even though the sun itself isn't visible, you can read a book in the shade without difficulty. You can walk through it without stumbling. The shade is illuminated by the brightness of the rest of the sky. On the moon, none of that holds true. A shadow on the lunar surface is dark in a way no shadow on Earth ever is. The walls of a lunar crater lying outside direct sunlight receive almost no scattered light from above, because there's no atmosphere to do any scattering. The contrast between lit ground and shadowed area becomes enormous. Stand at the edge of a lunar shadow, and one boot can sit in full sunlight, while your other boot, a foot away, sits in pitch darkness. This is the world without an atmosphere. Light still arrives from the sun, but it does only what light does in the complete absence of scattering. It travels in straight lines and stops wherever it strikes something solid. There's no overall glow, no ambient illumination. There's only direct beam and shadow, with nothing in between. Applying that same principle to nighttime gives us the central question of this entire piece. The dark sky we see on Earth at night is the sky we'd see at any time, day or night, if our planet had no atmosphere at all. The atmosphere reveals only daylight's bright version of itself, by scattering the sun's light around the sky. At night, with the sun on the far side of the Earth, the atmosphere becomes effectively transparent overhead. Through it, we see the universe directly, and the universe viewed directly turns out to be mostly dark, with a light sprinkling of stars. That sprinkling is precisely what we have to explain. Why so few visible stars, in a universe that by every other measure should be packed full of them? The atmosphere isn't hiding anything from us at night. We can see straight through it clearly. If the universe were a uniform bright background, we'd see it as a uniform bright background, atmosphere or no atmosphere. The atmosphere lights the daytime sky. It does not darken the nighttime sky. The dark night sky is the universe's own face, and that face is what we now have to properly understand. But before moving to the cosmic explanation, it helps to clear up one more small, practical confusion. Many people, looking at photographs of planets taken from space, notice that the backgrounds of those images are completely black, with no stars visible at all. This seems strange. Surely the stars are out there, in every direction. Why don't the cameras see them? The answer to that particular question has nothing to do with the universe. It's entirely about how cameras work. Almost everyone has seen photographs of planets and moons taken from spacecraft. The famous Apollo images show astronauts on the lunar surface, the gray ground stretching toward the horizon, the sky above completely black. Photographs of Saturn from passing probes show the planet in stunning detail, rings stretching out around it, suspended against a background of pure, unrelieved black. Photographs of Earth from orbiting spacecraft show the curve of the planet glowing against the darkness of space, with no stars visible behind it at all. The pattern is consistent. Wherever the foreground is bright, the background appears featureless. This often raises a natural question. If the universe really is full of stars in every direction, why aren't any of them visible in these photographs? Is the universe actually that empty once you get far enough from Earth's atmosphere? The answer is simpler than it might initially seem, and it has nothing to do with the universe being empty. It has everything to do with how cameras work and what they have to do in order to produce a usable image. Every camera, whether in space or on the ground, has to make a choice about how much light to collect before forming an image. This choice is governed by exposure, essentially a measure of how long the camera's sensor or film gathers light before the image is read out and recorded. A short exposure gathers little light, freezing fast motion and preserving detail in bright subjects. A long exposure gathers far more light, revealing faint sources, but also blurring motion and saturating anything bright. The trade-off between these two extremes is a fundamental fact of photography, full stop. When a spacecraft camera photographs Saturn's surface, the situation is fairly straightforward. Saturn is brilliantly lit by sunlight. The planet is, by an enormous margin, the brightest thing in the field of view. The cloud bands are clearly visible. The rings are clearly visible. The contrast across the planet's surface is high. To capture that detail, the camera must use an exposure short enough to preserve the highlights. If the exposure runs too long, the planet saturates the sensor, turning into a white, featureless blob, and the carefully designed instrument fails at its primary purpose. A short exposure suited to Saturn is far too short to ever reveal background stars. The stars are fainter than the planet by factors of 10,000 or more. In the brief moment the shutter stays open, the stars simply don't deposit enough light on the sensor to register at all. They sit below the noise floor of the camera. They contribute zero detectable signal. The result is a perfectly exposed image of Saturn, suspended against a background that records as zero light, which renders, in the final image, as solid black. This isn't the camera failing. This is the camera succeeding exactly at what it was asked to do. The black background isn't a claim by the camera that space is empty. It's a direct consequence of the exposure choice required to capture the bright planet correctly. If the same camera were instead instructed to take a long exposure suited to revealing background stars, Saturn would saturate completely and lose all its detail. The image would show some stars faintly and a large bright blob where the planet used to be useless for studying Saturn, and equally useless for studying the stars, because Saturn's overwhelming brightness would scatter light through the optics and contaminate the entire frame. So the engineers and astronomers planning these missions don't even attempt both kinds of image at once. They choose the exposure that serves the scientific purpose at hand. For planetary imaging, that almost always means short exposures, which means apparently starless backgrounds. The stars are still there. The camera simply can't see them at the same time as the planet. The same principle explains why the Apollo photographs from the lunar surface rarely show stars. The astronauts were photographing during lunar daytime. The ground was brilliantly lit by direct sunlight, with no atmosphere to soften the contrast. The white spacesuits worn by the astronauts reflected sunlight with high efficiency, effectively becoming miniature suns within the frame. The cameras carried by the crews were configured for exactly these bright subjects. The exposures were short. The stars overhead, dim by comparison, never had any realistic chance of registering on the film. The result was photographs of astronauts on a brightly lit surface, with the sky above appearing as solid black. This detail is sometimes pointed to by people who doubt the authenticity of the Apollo missions, who argue that the absence of stars proves the photographs were staged. The argument doesn't hold up. The absence of stars in those photographs is exactly what one would expect from images taken in lunar daytime with appropriate exposure settings. The presence of stars would have been the surprising, suspicious detail. The cameras did exactly what the physics of photography requires of them. There are a small number of exceptions. A handful of Apollo photographs taken with longer exposures, away from the brightest reflective surfaces, do show faint stars in the background. These are uncommon, because the practical purpose of the cameras was documenting the astronauts and their geological work, not cataloguing the celestial background. But where the exposure happened to be right, the stars appear exactly as they always have. The universe, photographed appropriately, is anything but empty. When cameras in space are pointed at regions of sky with no bright foreground and given long exposures and high sensitivity, the resulting images are extraordinary. Long-exposure images from orbiting telescopes show fields of galaxies so dense that the eye can't easily count them. In some images, taken with the most sensitive instruments and the longest exposures, every small patch of sky contains many thousands of distant galaxies, some of which themselves resolve into clouds of individual stars. A region of sky no larger than a small fingernail held at arm's length can contain tens of thousands of galaxies, each one containing hundreds of billions of stars. Images of this kind have transformed how astronomers think about the universe. They show, with full photographic clarity, that the cosmos is densely populated in every direction. The empty-looking regions of the night sky, as seen by the naked eye, aren't actually empty. They're simply full of objects too faint for the eye to detect. With sufficient sensitivity, those regions fill in with structure. The universe is rich. The eye is the limit. There's one more piece of this story worth mentioning. When astronauts photograph the night side of Earth from orbit, using appropriate cameras and exposures, the images that come back show the Milky Way arching across the heavens in spectacular clarity. The same Milky Way that's hard to make out from cities on Earth, washed out by light pollution and atmospheric haze, becomes overwhelming when photographed from above the atmosphere with the right equipment. The orbital night sky is not dark to a sufficiently sensitive camera. It's full of stars, full of structure, full of the bright band of our home galaxy. The blackness in the planetary images reflects which exposures the engineers chose, not a description of what's actually there. So we can set aside the impression that the universe is empty just because certain photographs make it look that way. The photographs are honest about their exposures, but they aren't transparent about what those exposures imply. The universe is densely populated. The stars are everywhere. The cameras simply can't, in a single image, record both a bright planet in the foreground and the dense stellar background behind it. But this only sharpens our central question. If the universe really is densely populated in every direction, and if our own atmospheric night sky is a transparent window onto that universe, why is the night sky we actually see still mostly dark? Long-exposure cameras show galaxies everywhere. Our naked eyes show only a few thousand stars and an enormous expanse of dark. The contradiction hasn't gone away. It has only sharpened. Why is the night sky dark when sufficiently sensitive instruments reveal structure in every direction we point them? That's the question the next stretch of our journey takes up directly. It's a question that has been asked, in one form or another, for hundreds of years, and until quite recently it had no good answer. The puzzle of the dark night sky has been noticed for a very long time. It isn't a modern question at all. Astronomers and natural philosophers wrestled with it for centuries before the modern resolution finally arrived. In its most basic form, the question can be stated cleanly, and once stated, it tends to stick with whoever first hears it. It feels like the kind of question that ought to have a simple answer, and yet, attempt after attempt, the answer keeps slipping away. Let's state it carefully. Assume the universe is unbounded in space. That is, assume there's no edge to it, and space simply goes on in every direction without limit. Assume also that the universe contains stars distributed throughout it, with some average density per unit volume. There may be local clumps and gaps, regions denser or sparser than average, but on the largest scale, assume the distribution is roughly uniform. Assume finally that the universe is eternal, that it has existed forever, and the stars have been shining for as long as they've existed. Now ask, what should the night sky look like from anywhere inside such a universe? The reasoning unfolds straightforwardly. Imagine standing inside this universe, looking outward. Consider a thin spherical shell of space at some given distance from you, with some thickness. That shell contains a certain number of stars proportional to its volume. If the shell sits twice as far away, it has roughly 4 times as much volume at that same thickness, because the surface area of a sphere grows with the square of its radius. So a more distant shell contains more stars in total than a nearer one. But the stars within that more distant shell are individually fainter. Each star's apparent brightness, as seen by the observer, falls off with the square of distance. A star twice as far away appears 1/4 as bright. A star 3 times as far appears 1/9 as bright. Now combine these two facts. The number of stars in a shell grows as the square of distance. The brightness of each individual star falls as the inverse square of distance. The two effects cancel out exactly. Each shell, however distant, contributes the same total light to the observer. The closer shells hold fewer stars, but each star contributes more brightness. The more distant shells hold far more stars, but each contributes correspondingly less. The total light from any given shell, summed across all its stars, comes out the same regardless of distance. If the universe is infinite, then there are infinitely many such shells, each contributing an equal amount of light. The total light arriving at the observer, summed across all shells, would diverge. It would be infinite. In practice, that exact divergence wouldn't quite happen, because stars aren't true point sources. Eventually, in any given direction, the line of sight reaches a shell where some star is large enough to fully cover that line of sight entirely. From that distance outward, the line of sight is blocked by that star's disk, and any stars farther out in the same direction sit hidden behind it. So the brightness in any particular direction is bounded by the surface brightness of the nearest star along that line. But because stars exist everywhere, every direction is eventually blocked by some star, somewhere, and the surface brightness of an average star stays the same regardless of distance, because the two scaling effects keep cancelling. The conclusion, in an infinite, static, eternal universe filled with stars, the night sky shouldn't merely be bright. It should be, everywhere, as bright as the surface of an average star. There should be no dark patches anywhere at all. Every direction should eventually terminate on a stellar surface. The night sky should glow uniformly, with the brightness of a sun, in every direction at once. To sharpen this intuition further, picture an analogy from a more familiar setting. Imagine standing in the middle of a vast, uniformly thick forest, trees of identical size growing at regular intervals in every direction. Look outward through the trees. In any direction you choose, your line of sight will eventually be blocked by a trunk, because the forest extends infinitely and trees are everywhere. You cannot see out of the forest, regardless of which way you look. Nearby trees occupy larger apparent sizes, but distant trees are far more numerous within any narrow cone of vision, and the two effects balance out enough that the forest looks roughly uniform in every direction. You see trunks everywhere. There's no gap through which the outside world becomes visible. The geometric argument for a bright sky in a stellar universe is exactly this argument, applied to stars instead of trees. Each star, like each tree, occupies some small apparent size in the sky. There are many stars in any given direction. Their apparent sizes, summed across all distances, should fill the sky completely, in every direction. The eye looking outward through a forest of stars should see only stars, with no dark gaps at all. This forest analogy is useful precisely because it makes vivid what would actually have to be true for the dark sky we observe to make any sense. 4 gaps to appear in your line of sight. The forest would have to be young, or finite, or somehow stretching out from beneath you even as you look at it. None of those conditions describes an ordinary forest. The eternal, static, infinite picture of the universe is, in this sense, like an old and unchanging forest. The actual universe is more like a young forest still growing into itself, with light still arriving from new directions as time passes. The forest floor itself spreading underneath the trees even as they grow. The gaps we see between stars are exactly the kind of gaps such a young growing forest would naturally have. But that's not what we see in the simple analogy, and that's not what we see in the sky either. The night sky is dark, the stars are scattered points. The brightness is far less than that of a true stellar surface. Something in the setup of this argument has to be wrong. This puzzle, in essentially this exact form, was already being noticed by careful observers and thinkers as far back as the 17th century. The argument is straightforward enough that anyone willing to work through the geometry can derive it independently. Several writers, including some of the great natural philosophers of that era, noted that the dark night sky seemed to require either a finite universe or some more complicated arrangement of stars than a simple uniform distribution or some other auxiliary feature absent from the basic picture. By the early 19th century, the puzzle had been taken up and given thorough mathematical treatment by a German astronomer. He laid out the argument carefully and proposed his own resolution, which we'll examine shortly. The puzzle has carried his name ever since. Even though he wasn't the first to notice it, he simply gave it the clearest statement and the most prominent attention of his era. For roughly the next century, the paradox was treated mostly as a curiosity, a logical puzzle, awaiting a clever auxiliary assumption. Various proposed fixes came and went, each attempting to preserve the basic picture of an eternal universe filled with stars, while adding some feature meant to explain the dark sky we actually observe. None of these proposals quite worked. Each one proved vulnerable to a counterargument that brought the paradox right back. The puzzle persisted as a quiet, unresolved itch at the back of cosmological thought. It was only in the 20th century, with the discovery of cosmic expansion and the realization that the universe has a finite age, that the paradox finally received a clean, physically grounded resolution. But before that resolution, every proposed answer fell short, and the reason each one fell short is itself instructive, because it shows us what the question is really asking. The question isn't really about stars at all. It's about the structure of the universe at its very largest scales. The dark sky is a window onto cosmology, even though it doesn't look like one at first glance. To see why, consider what we've just established. The simple geometric argument shows that, in an infinite, static, eternal stellar universe, the sky should be bright. The sky is dark. Therefore, at least one of those three assumptions, infinite, static, or eternal, must be wrong. The dark sky itself is evidence about the structure of the universe. It is data. The natural philosophers of past centuries didn't have the tools to follow this evidence cleanly. They tried instead to preserve the infinite, static, eternal universe by tacking on extra features: dust scattered between the stars, a finite count of stars within some finite region, a hierarchical distribution of stars nested in clusters within clusters. Each of these proposals attempted to dissolve the paradox without abandoning the underlying picture. Let's look at each one and see why each ultimately fails. The first proposed resolution carries a certain intuitive appeal. It runs something like this: yes, the universe may be infinite and filled with stars. Yes, the geometric argument shows that every line of sight should eventually meet a star. But the lines of sight aren't actually clear. The space between the stars isn't empty. It's filled with absorbing material, dust, gas, opaque debris. This material lies between us and the most distant stars and simply blocks their light. The light from very distant stars never reaches us because something in the way absorbs it first. The dark sky, on this view, is a kind of cosmic fog. We see only the nearby lights, and the rest hides behind a vast interstellar veil of dust. The appeal here is that it has some basis in reality. There genuinely is dust and gas in the space between stars. Some regions of our own galaxy are dark precisely because of this material, which absorbs starlight from objects behind it. Look at images of the Milky Way and you'll see dark lanes threading through the brighter band of stars. These lanes aren't gaps in the starfield. They're regions where interstellar dust is dense enough to obscure the stars behind it. The dust is real. The absorption is real. It seems entirely natural to ask whether enough dust, distributed throughout the universe, could absorb enough light to leave the night sky dark. But on closer inspection, the proposal fails. The reason is thermal, and it's worth working through carefully, because it reveals something important about how the paradox really operates. Suppose, as the proposal suggests, that the space between stars is filled with absorbing dust. Now ask what happens to the light the dust absorbs. It doesn't simply vanish. Energy is conserved. The light's energy transfers to the dust grains, which grow slightly warmer as a result. Their temperature rises. As their temperature climbs, they begin radiating energy outward as their own emitted light. The hotter they get, the more they radiate. They reach a thermal balance once the rate at which they absorb energy from incoming starlight equals the rate at which they emit their own radiation. In an infinite, eternal universe, where starlight has been arriving for an infinite span of time, the dust grains eventually reach an equilibrium temperature at which they radiate exactly as much energy as they absorb. That equilibrium temperature depends on how much starlight is arriving in the first place. If the surrounding universe is filled with stars whose total surface brightness matches that of an average star, the dust eventually reaches a temperature whose blackbody emission matches the brightness of that average stellar surface. At that point, the dust glows just as brightly as the stars themselves. The night sky becomes bright again. The dust is no longer a dark obstruction at all. It has become, itself, a glowing surface, and the sky fills with its glow. So the dust proposal doesn't actually solve the paradox. It only redistributes where the brightness comes from. Instead of seeing stars directly, we'd see glowing dust instead. The total brightness of the sky would still match that of a stellar surface in every direction. The dark sky remains unexplained. This is the first failure. The dust resolution cannot work in an infinite, eternal universe, because thermal equilibrium inevitably drives the dust to the same effective temperature as the stars, and the sky stays bright either way. A second proposal tries a different angle entirely. Maybe the universe doesn't actually contain infinitely many stars. Maybe the universe is finite. Stars exist out to some particular distance, and then nothing exists past that boundary. Or maybe infinitely many stars exist, but arranged in a way that effectively concentrates them near us. Either way, the integral of starlight over all directions might come out finite, leaving the sky dark. This proposal points in a genuinely useful direction, but it isn't quite right either. The reason is observational. Modern observation, especially with sensitive telescopes, has shown that the universe isn't arranged in a way that simply runs out of stars at some fixed distance. On the contrary, the deeper we look, the more galaxies we find. The most distant accessible regions of the cosmos are packed with galaxies, much like our own local region. There's no observed edge beyond which stars simply cease to exist. So the simple version of the finite universe proposal doesn't match what we actually see. There's a more sophisticated version of this idea, sometimes called the fractal or hierarchical distribution. The idea is that stars are arranged in clusters, those clusters within larger clusters, and so on, with the effective density of stars dropping as you look at progressively larger scales. If the distribution is hierarchical in just the right way, the integral of starlight over all distances becomes finite even within an infinite universe, because the density of contributing stars drops faster than the geometric scaling can compensate for. The sky stays dark. This particular proposal is mathematically valid for certain specific distributions. You can construct the math to make it work, but again, observation doesn't support it. When astronomers survey the universe at sufficiently large scales, they find the distribution of galaxies becomes statistically homogeneous. There are clumps and voids on smaller scales. The cosmic web carries structure on the order of tens to hundreds of millions of light-years, but beyond that scale, the universe is roughly uniform. There's no continuing fractal hierarchy that would keep diluting stellar density the farther out you look. The arrangement required to dissolve the paradox simply isn't what the universe actually does. A third proposal, sometimes raised in older discussions, points out that even within an infinite stellar universe, the actual amount of light reaching our location depends on the average surface brightness of stars, the average density of stars, and the effective volume of universe contributing light. If those numbers were arranged just right, perhaps the total brightness could come out finite. But this runs into the same problem as the dust proposal. In an eternal universe with continuous starlight, any arrangement that doesn't absorb or hide light eventually produces a sky filled with the surface brightness of stars. The geometric argument is robust against this kind of patching, so we're left, in summary, with three failed resolutions. Dust between the stars fails because the dust eventually thermalizes and glows just as brightly. A finite count of stars fails because observations show the universe is densely populated wherever we look. Hierarchical distributions fail because the actual large-scale distribution is homogeneous, not endlessly fractal. None of these auxiliary features can do the work the paradox demands. Notice what all three failed proposals share. They all try to preserve an eternal, static universe. They all assume the universe has existed forever and remains unchanging at the largest scale. They differ only in what extra structure they propose adding to that picture. None of those additions can produce a dark sky within an eternal, static universe filled with stars. The lesson slowly emerging from these failures is that the universe itself cannot be both eternal and static. If we want to keep the dark sky we actually observe, we have to give up one or both of those assumptions. The auxiliary features can't rescue the simple picture. The simple picture itself has to change. This is where the real resolution finally begins. Once we let go of eternal and static, the dark sky becomes natural rather than mysterious. The actual universe isn't eternal. It has a finite age. The actual universe isn't static. It's expanding. With those two facts in hand, the geometric argument from earlier breaks down in a clear, precise way, and the dark sky we observe falls right out as a straightforward consequence. The discovery that the universe has a finite age and is expanding arrived in the early 20th century through a combination of theoretical work in general relativity and observational work on the spectra of distant galaxies. We won't retrace the full history of that discovery here, because it belongs to a much larger story of its own. But the key facts can be stated cleanly, and they're exactly what we need to resolve the paradox we've been carrying. The universe had a beginning, some great span of time ago, under conditions vastly different from the ones we see now. The universe came into existence. Since then, it has been expanding and cooling. The galaxies, stars, and planets we observe today formed during this long expansion. Before stars existed, the universe was filled with hot gas. Before the gas, even hotter, plasma. Before the plasma, more primordial states we're still working to fully understand. But for our purposes, the central point is simply this: the universe is not eternal. Its history is finite. The universe is also not static. The space between galaxies stretches over time. Galaxies more distant from us recede faster than nearer ones, and the rate of recession grows with distance. This is the expansion of the universe, and it carries direct consequences for light traveling between galaxies. With these two facts established, the paradox dissolves. Here's how. The geometric argument that produces an everywhere bright sky implicitly assumes there has been enough time for light from arbitrarily distant stars to have already reached us. In an eternal universe, that assumption is automatic. Every star, no matter how far away, has had infinite time to send light in our direction. The light has had ample time to arrive. The integral of starlight over all distances is well defined, and it diverges, and the sky should be bright. But if the universe is only some finite age, that automatic assumption simply fails. Light from a star 1 light-year away takes 1 year to reach us. Light from a star 1 billion light-years away takes 1 billion years. Light from a star 10 billion light-years away takes 10 billion years, and light from any region of the universe whose distance is such that the journey would take longer than the universe's current age hasn't arrived yet at all. The universe hasn't existed long enough for that light to make the trip. From our point of view, in the directions where the most distant possible sources sit, the sky is empty because the light is still in transit. It hasn't gotten here yet. It may never get here. This is the heart of the resolution, and it's worth restating in a different way. When you look out into space, you're also looking back in time. The light reaching your eye from a star 10 light-years away left that star 10 years ago. The light reaching you from a galaxy 10 million light-years away left that galaxy 10 million years ago. The farther out you look, the further back in time you're seeing. And if you look far enough, you eventually reach a point where you're looking back to a time before the universe existed in its current form. Beyond that point, the line of sight doesn't run into a star at all. It runs into the universe's own youth. The far reaches of any line of sight then aren't regions of empty space, waiting patiently to be illuminated by distant stars. They are regions of the universe as it existed at very early times, when there were no stars yet, when the universe was filled only with hot gas or even hotter plasma, when the conditions that make stars possible hadn't yet developed. The light reaching us from those most distant regions is the light of the early universe itself, not of stars within it. This is precisely why the simple geometric argument fails. It implicitly assumed that every shell of space, at every distance, contained a population of mature stars. That assumption is false. The shells at very large distances contain the universe in its early prestellar state. They aren't filled with stars at all. They can't contribute starlight to our sky, because the universe at those distances and times had no starlight to contribute in the first place. Already, just from this single correction, the predicted brightness of the sky drops dramatically. The shells that should have contributed the most stars, because they have the most volume, turn out to contribute none. The geometric divergence stops. The integral of starlight over all distances becomes finite. because only the relatively nearby shells, where the universe is old enough to actually have stars, contribute anything to the total, and the combined contribution from those nearby shells comes out far below the surface brightness of a typical star. The sky comes out mostly dark. The portion of the universe close enough that its light has had time to reach us is called the observable universe. It sits within our cosmic horizon, a boundary set by the speed of light, combined with the age of the universe. Beyond that horizon, the universe may well continue with stars and galaxies and structure, but none of its light has yet had time to arrive. From our vantage point, the observable universe is finite. Even if the universe at large is infinite, we see only what's close enough for the light to have made the journey. This alone is enough to dissolve the dark sky paradox in its strongest form. The geometric argument predicted infinite brightness from an infinite stellar universe. The finite age of the universe means there is no infinite stellar contribution available. Only a finite, accessible portion of the universe can contribute light to our sky, and that finite portion doesn't add up to a full stellar surface brightness when integrated together. The sky is dark because the universe simply hasn't existed long enough to fill every available direction with starlight. But there's more to the story. The finite age is the dominant factor, but it isn't the only one. There's a second factor that adds further to the darkness, and that factor is the expansion of space itself. Space in our universe isn't static, it's stretching. Galaxies aren't flying apart through some fixed background. The background itself is growing. The distance between two distant galaxies, neither of which is actually moving relative to its own local environment, increases over time because the space between them is continually being added to. This is the expansion of the universe, and it ranks among the most thoroughly confirmed facts in all of modern cosmology. This expansion carries direct consequences for light. When a photon is emitted by a distant source and travels across the expanding universe to reach us, the photon's wavelength stretches along with the space it's traveling through. By the time it arrives, its wavelength is longer than when it departed. The longer the journey, the more it's been stretched. This stretching is the cosmological redshift, and it's responsible for the fact that light from very distant galaxies arrives shifted toward the red end of the spectrum. For sufficiently distant sources, the redshift becomes extreme. Light emitted as visible light billions of years ago can, by the time it arrives, be redshifted into the infrared, the microwave, or even longer wavelengths. The photon is still there, the energy is still being delivered, but that energy no longer sits within the visible band. The eye, sensitive only to a narrow window of wavelengths, no longer detects it at all. The consequence is that even regions of the universe whose light has had time to reach us contribute less to the visible brightness of the sky than a static calculation would suggest. Light from very distant sources, which in a static universe would arrive with its original visible wavelengths intact, instead arrives shifted out of the visible band entirely. The optical brightness of the sky is further diminished by this cosmological redshift, layered on top of the limit already imposed by the universe's finite age. These two effects, finite age and expansion-driven redshift, work together to make the night sky dark. The finite age cuts off contributions from very distant regions entirely. The redshift further diminishes the contribution from the distant regions that do manage to contribute. The integrated optical brightness of the sky comes out far below the brightness of a stellar surface. The dark sky we observe is exactly what such a universe naturally produces. There's one more effect worth noting here. The expansion of the universe isn't simply ongoing at some constant rate. It's accelerating. The rate of expansion increases with time, driven by a component of the universe we don't yet fully understand, called dark energy. As a result, the most distant regions of the universe recede from us at rates that grow with time. There exists a boundary called the cosmic event horizon, beyond which light, leaving a source today, will never reach us, because the space between us is being added to faster than the light can ever cross it. This means the universe we can ultimately see isn't merely bounded in time, it's ultimately bounded in space as well. Even given infinite time, there are sources whose light remains permanently out of reach. The sky will never fill in with starlight from those regions, because no signal from them can ever arrive. The night sky's darkness, in its deepest sense, is a permanent feature, not a merely temporary one. Taken together, the dark sky becomes entirely natural. The universe has a finite age, so light from regions beyond the horizon hasn't had time to arrive. The universe is expanding, so the light that does arrive from distant sources gets stretched out of the visible band. The expansion is accelerating, so some sources are permanently inaccessible to us, full stop. The geometric argument for a bright sky required a universe that was eternal, static, and uniformly filled with mature stars. The actual universe is none of those three things. The sky we see is precisely the sky such a universe naturally produces. We've reached the resolution. The dark night sky isn't a paradox in our universe. It's a direct consequence of how our universe is actually arranged. It tells us, by its very darkness, that the universe had a beginning, that space is expanding, and that horizons exist beyond which we simply cannot see. The sky is data. The dark is evidence. Every patch of darkness between the stars carries a record of cosmic structure on the very largest scales. There's one more piece of this story worth examining. Though we've said that even regions whose light does reach us send some of that light in wavelengths outside the visible band, that suggests the universe viewed in other wavelengths might look dramatically different from the dark sky we see with our own eyes. And it turns out that's true, in a genuinely striking and beautiful way. The cosmological redshift deserves a closer look, because it carries with it a lesson about what's actually happening to light from distant places. The redshift isn't simply a label we attach to light that arrives looking redder than it left. It's the consequence of a real physical process, the stretching of space itself, and it has implications reaching well beyond the dark sky question we've been working through. Imagine a photon emitted by a distant galaxy. That photon carries a certain wavelength at the moment of emission, set by whatever physical process produced it. Hydrogen atoms within the galaxy emit light at specific characteristic wavelengths, and so do other elements. These characteristic wavelengths are well known and universal. The physics producing them is the same here as anywhere else in the cosmos. Now the photon travels across cosmic space toward us. While it's in transit, the space it moves through is itself expanding. That expansion doesn't exactly push the photon. It doesn't add energy to it directly. What it does is stretch the distance the photon must cover, and that stretching applies to the photon's wavelength just as it applies to the path length. By the time the photon reaches our detectors, its wavelength has grown longer than it was at emission, in direct proportion to how much the universe expanded during that photon's journey. The factor by which the wavelength stretches is called the redshift. A redshift of 1 means the wavelength has doubled. A redshift of 2 means it has tripled. A redshift of 9 means it's been multiplied by 10. The most distant galaxies observed carry redshifts around 10 or more, meaning their light arrives stretched by a factor exceeding 10 compared to its original wavelength. Light that left those galaxies as visible light arrives in the infrared. Light that left as ultraviolet arrives as visible. The entire spectrum has shifted. This stretching tells us about the universe's past. The further out we look, the further back in time we're looking, and the more the universe has expanded since that light was emitted. A galaxy's redshift therefore measures how long ago its light departed, and equivalently, how much the universe has expanded since. By cataloging the redshifts of many galaxies, astronomers trace the history of cosmic expansion directly. The most extreme case, in a sense, is the cosmic microwave background. This is leftover light from a much earlier era, when the universe was about 380,000 years old, and the hot plasma filling it had finally cooled enough for electrons and protons to combine into neutral hydrogen atoms. At that moment, the universe became transparent to photons for the very first time, and the photons present in that plasma began their long journey through cosmic space. Those photons have been traveling ever since, for many billions of years. The universe at that ancient moment was hot, roughly 3,000 degrees. The photons that decoupled from the plasma then carried a spectrum characteristic of that hot state, peaking in the visible band. If we could somehow have observed those photons at the very moment of their release, the sky would have glowed a bright orange-white in every direction, with the temperature of a relatively cool stellar surface. But the universe has expanded by a factor of more than 1,000 since that moment. The photons arriving at us today have been redshifted by that same factor of more than 1,000. Their wavelengths have stretched correspondingly. Light that began as visible has been pulled all the way into the microwave region of the spectrum. The peak of the spectrum, originally in the visible range, now sits at a wavelength of roughly 1 millimeter. The temperature of the radiation, as measured today, is about 2.7 degrees above absolute zero. It's no longer hot orange light. It's a soft, cold microwave glow. This radiation fills the entire sky. It arrives from every direction. It's the redshifted afterglow of the early universe, and it ranks among the most thoroughly studied features in all of modern cosmology. It is the dark night sky, rendered visible at a wavelength your eye simply cannot perceive. If your eyes were sensitive to microwaves of the right wavelength, you would see the entire sky glowing softly and uniformly, with no dark patches anywhere at all. The night sky, in microwaves, is not dark. It's full. This is one of the most beautiful aspects of the resolution we've been working through. The dark sky we see is dark only within the optical band, the narrow window of wavelengths human eyes happen to detect. In other wavelengths, the sky overflows with light. The cosmic microwave background is the most uniform of these other wavelength skies, but is far from the only one. The sky in infrared is full of cool stars, brown dwarfs, dust clouds glowing with re-radiated starlight, and the warm cores of forming galaxies. The sky in radio waves is full of pulsars, distant active galaxies, and a steady background of unresolved sources. The sky in X-rays is full of black hole accretion regions, hot gas in galaxy clusters, and the surfaces of neutron stars. The sky in gamma rays is full of bursts and steady high-energy sources. The universe, in other words, is alight across the full electromagnetic spectrum. It's only in the optical band, the narrow window visible to our particular biology, that the sky appears mostly dark. And even that optical darkness isn't truly an absence. It's the layered result of several factors working together. The finite age of the universe, which means most lines of sight reach back to prestellar times. The expansion of space, which redshifts light from distant sources out of the visible band entirely. The cosmic event horizon, beyond which light can never reach us at all. And the finite lifetime of individual stars, which means even within the observable region, Currently glowing stars represent a smaller population than the total stellar history might otherwise suggest. Each of these factors carries its own story, and together they make the optical darkness of the night sky a particular signature of our specific universe. A different universe, with different parameters, would have a different night sky entirely. A universe with a much longer age might give light from far more distant regions time to arrive, producing a brighter night sky. A universe with no expansion wouldn't redshift its light out of the visible band, and would accumulate more visible starlight over time. A universe with very long-lived stars would maintain a much larger population of currently glowing stars, increasing the total optical brightness. Our universe is the one we actually have. It's finite in age, expanding, and inhabited by stars with finite lifetimes. Its night sky is dark in the optical band as a direct consequence of exactly these properties. The dark sky is therefore a kind of measurement. By looking at it, we can read out features of the underlying cosmology. We know, from the very darkness of the night sky alone, that the universe is not eternal. We know, more precisely, from quantitative observations of the cosmic microwave background and the redshifts of distant galaxies, the actual age and expansion history of the universe in considerable detail. The dark sky was the first hint of these facts. Modern cosmology fills in the rest of the picture quantitatively. Take a moment to sit with this. The dark sky overhead is not empty. It's full of light at wavelengths your eyes don't see. It's full of evidence about how the universe began and how it has evolved. It's full of history, encoded in photons that have been traveling for billions of years to reach the small patch of biological tissue that finally detects them. The darkness is itself information. It's the universe telling you that it had a beginning, that space is expanding, that horizons exist, and that the stars themselves are mortal. All of that, written into the gap between the stars overhead. There's a final, gentler observation worth making here. The optical darkness of the night sky is partly a fact about us. We're sensitive only to a narrow window of the electromagnetic spectrum, roughly between 400 and 700 nanometers, a small slice of the full range over which photons can carry information. Different organisms have different windows. Some insects see further into the ultraviolet. Some snakes detect infrared in addition to visible light. None of these biological windows covers more than a small fraction of the full electromagnetic spectrum. The universe contains light across an enormous range, and any single biological sensor catches only a sliver of it. For our particular sliver, the night sky is mostly dark. For other slivers, it would look completely different. A creature sensitive to microwaves would see a uniformly glowing sky, the cosmic background radiation, in all directions. A creature sensitive to certain infrared bands would see a sky full of cool stars and dust clouds. A creature sensitive to X-rays would see a sky punctuated by bright points where black holes accrete matter, and broad regions where hot gas in galaxy clusters glows softly. The night sky depends on who's looking. This is the deepest sense in which the dark sky isn't really a property of the universe, but of our relationship to it. The universe is full of light. We see only a small fraction of it, and the rest passes through us, or past us, without ever registering at all. The dark between the stars is, in part, simply a measure of how narrow our eyes happen to be. With wider eyes, the dark would fill in with the rest of the spectrum, and there would be no question of why the sky is dark in the first place. But we have the eyes we have, and what they tell us, in the language they speak, is that the universe is young, expanding, and structured. The dark sky is their report. There's one more aspect of the cosmological redshift worth mentioning before moving on. The redshift is sometimes confused with the Doppler effect, the more familiar shift in pitch or wavelength caused by relative motion between a source and an observer. The two are related but not identical. The Doppler effect arises when a source moves relative to its surroundings through a fixed background. The cosmological redshift arises because the background itself is changing, with the source and observer each remaining essentially at rest within their own local environments. The light stretches, not because the source is moving through space, but because space itself is growing while the light is in flight. This distinction matters for understanding what the universe is actually doing. The galaxies receding from us aren't flying through static space like debris thrown from an explosion. They sit in their local environments, more or less stationary, relative to nearby gas and galaxies, while the space between them grows over time. The recession isn't motion through space. It's the stretching of space between objects. A photon in flight participates in that stretching directly, and its wavelength grows accordingly. The mathematical framework describing this is general relativity, the theory of gravity that replaces older Newtonian descriptions whenever very large distances, very strong fields, or very fast motion come into play. In general relativity, the geometry of space and time is itself a participant in physics, not merely a fixed stage on which physics happens. Matter and energy curve space and time. Space and time, in turn, shape the motion of matter and energy. When the geometry of space expands, light traveling through it shares in that expansion, and its wavelength grows accordingly. You don't need to fully grasp this in order to make peace with the dark sky. But it helps to know the redshift rests on solid physics, well tested in numerous independent ways, from the precise timing of distant pulsars, to the gravitational lensing of light by intervening galaxies, to the steady ticking of clocks at different altitudes within Earth's own gravitational field. The redshift is part of a coherent picture, not a patch bolted on to make the math come out right. If we step beyond the optical window entirely and consider the universe across other wavelengths, the picture changes completely. The dark night sky seen by the naked eye gets replaced by a series of skies, each with its own structure, its own brightness patterns, its own distinct population of sources. Each wavelength band reveals something different about what's actually out there. Taken together, they paint a picture of a universe that is anything but dark. Begin with the infrared. Infrared light carries wavelengths longer than visible light, roughly between 1 micrometer and a few hundred micrometers. It's invisible to human eyes, but detectable with specialized instruments, often cooled to very low temperatures, since warm components within the detector itself would otherwise drown out the faint infrared signals from the sky. Infrared telescopes operating in space, kept cold and shielded from atmospheric interference, have produced some of the most striking images of the universe ever captured. In infrared, the universe overflows with cool stars, red dwarfs, far more numerous than sun-like stars, but much dimmer in the visible band, shine brightly in infrared. Brown dwarfs, not quite massive enough to sustain stable hydrogen fusion and therefore invisible in the optical band entirely, become visible in infrared thanks to their residual internal heat. Even cooler objects, like the warm cores of forming planets, can be detected this way. The infrared sky holds a rich population of sources the optical sky simply never reveals. Beyond cool stars, the infrared sky reveals the structure of cosmic dust, the same dust grains lying between stars, the same dust we earlier considered as a possible solution to the dark sky paradox. get heated by surrounding starlight, and re-radiate that energy in the infrared. Dust clouds that look dark and obscuring in the visible band glow brightly in infrared images. The dark lanes of the Milky Way, appearing as black gaps in optical images, light up as luminous tendrils of warm dust when viewed in infrared. The galactic plane carries infrared structure, entirely hidden from optical view. The most distant galaxies, whose light has been redshifted out of the visible band by cosmic expansion, also emerge into view in infrared. Light originally emitted as ultraviolet or visible gets stretched by redshift into the infrared by the time it reaches us. Infrared telescopes can therefore see galaxies completely invisible to optical telescopes. Some of the most distant galaxies ever observed were found specifically through infrared instruments, because their light had been redshifted by factors of 10 or more, pushing their original ultraviolet emission into longer infrared wavelengths. Move further along the spectrum into the microwave band. Microwaves carry wavelengths from roughly a millimeter up to a meter or more. This band is dominated by the cosmic microwave background. We've already discussed the relic radiation from the early universe. The microwave sky fills with this background, glowing uniformly in every direction at a temperature very close to, but not quite exactly, 2.7 degrees above absolute zero. The small temperature variations across the sky, a few parts in 100,000, encode an enormous amount of information about the early universe. They've been mapped in exquisite detail by satellite missions, making this one of the most thoroughly studied skies in all of astronomy. Beyond the cosmic microwave background itself, the microwave sky also contains light from cold dust clouds, distant galaxies in dust-dominated phases of their evolution, and various other diffuse sources. It isn't merely a uniform glow. It carries structure across a wide range of scales, and that structure, carefully separated from the background, tells us about the distribution and evolution of matter across the universe. Now go in the opposite direction, toward shorter wavelengths. Beyond visible light lie the ultraviolet, then X-ray, then gamma-ray bands. Each carries its own distinct astronomy. In the ultraviolet, the sky is dominated by hot, young stars. Stars more massive and hotter than the Sun emit much of their light in ultraviolet, standing out brightly in ultraviolet surveys. Regions of recent or ongoing star formation glow particularly brightly. Young star-forming galaxies, dominated by hot massive stars, shine strongly in ultraviolet. In the X-ray band, the sky is dotted with extreme sources. Black holes accreting matter from companion stars or surrounding gas heat that in falling material to enormous temperatures, and the material emits intense X-rays before crossing the event horizon. Neutron stars, with surface temperatures in the millions of degrees, glow steadily in X-rays. Galaxy clusters contain hot gas at tens of millions of degrees, filling the space between cluster galaxies with a faint X-ray glow that maps out the cluster's gravitational well. Active galactic nuclei, where supermassive black holes at galactic centers actively accrete matter, rank among the brightest X-ray sources anywhere in the universe. In the gamma-ray band, the sky grows even more extreme. Gamma rays come from the most energetic processes the universe produces. The collapse of massive stars at the moment of a supernova explosion, the merger of compact objects like neutron stars, violent accretion onto supermassive black holes, and various exotic decay processes. Gamma-ray observatories detect bursts of these high-energy photons arriving from across the universe, sometimes from sources at staggering distances. The gamma-ray sky carries steady sources, punctuated by transient bursts, that rank among the most luminous events in the entire cosmos. Across the radio band, at wavelengths longer than microwaves, the sky reveals yet another rich population. Pulsars, the rapidly spinning remnants of supernova explosions, emit beams of radio waves that sweep across the universe like cosmic lighthouses. Cold hydrogen gas, the basic building material of galaxies, glows softly in a characteristic radio line at 21 centimeters, letting astronomers map the distribution of neutral hydrogen across galaxies and intergalactic space. Active galactic nuclei often produce powerful jets of plasma, emitting synchrotron radiation across a wide range of radio wavelengths, sometimes extending hundreds of thousands of light-years from the central galaxy. The radio sky has been mapped at many different wavelengths, each map showing a distinct population of sources. Beyond the electromagnetic spectrum entirely, the universe communicates through still other channels. Neutrinos, nearly massless particles that interact only weakly with ordinary matter, stream out of supernova. Accretion disks, and the nuclear furnaces at the centers of stars. Specialized detectors, often built deep underground or under ice to shield them from interference, occasionally register a neutrino interaction. The neutrino sky, slowly being mapped by these detectors, includes contributions from our own sun, from supernova in our galaxy and beyond, and from a faint, diffuse background originating in the early universe itself. Gravitational waves, ripples in the geometry of spacetime itself, offer another channel entirely. Massive objects accelerating through space, especially violent mergers between black holes and neutron stars, produce gravitational waves that propagate outward across the cosmos. Specialized detectors on Earth and in space register these waves as they pass through. The gravitational wave sky is only just beginning to be mapped, and it already reveals a population of compact object mergers that would otherwise be entirely invisible in any electromagnetic channel. Each of these channels comes with its own enormous engineering challenges. Building a detector sensitive to any particular wavelength band requires specialized materials, careful shielding from interfering signals, and often an unusual location. Some detectors operate from mountaintops, where the air above is thinnest. Some operate from balloons, well above most of the atmosphere. Some operate from orbit, entirely above the atmosphere. Some, like neutrino detectors, sit deep underground or beneath thick ice, where surrounding matter shields the detector from interfering particles. Some, like gravitational wave detectors, are kilometer-scale interferometers built into vacuum-sealed vaults, isolated from every conceivable source of vibration. The lengths astronomers have gone to in order to listen on each new channel are remarkable in their own right. Each new sensitivity required years of design and engineering, often with no guarantee anything would actually be detected once the instrument finally came online. The reward, in every case, has been a new view of the cosmos. The radio sky reveals structure the optical sky never shows. The infrared sky reveals dust-shrouded star formation, invisible to ordinary light. The X-ray sky shows the energetic processes surrounding black holes and neutron stars. The gamma-ray sky shows the most violent events known to physics. The neutrino sky carries information from the cores of stars and supernova that no electromagnetic channel can ever reach. The gravitational wave sky shows compact object mergers that produce little or no light at all. Each channel adds a new dimension to our picture of the universe, and the combined picture is far richer than any single channel could ever show on its own. Astronomers sometimes describe this as multi-messenger astronomy, because the universe sends its messages through multiple kinds of signal, not merely through electromagnetic light. The merger of two neutron stars, for instance, has been observed simultaneously in gravitational waves, gamma rays, X-rays, ultraviolet, visible light, infrared, and radio waves, with each channel providing different, complementary information about the same event. The visible light counterpart, in that case, is just one piece of a much larger story. The full picture requires combining every channel together. This is a useful frame for thinking about what the dark night sky actually is. It's the visible light channel of the cosmos, viewed from our particular planet by the naked human eye. It's a single channel of a multi-channel universe, viewed by a single kind of sensor from a single vantage point. The information available within that single channel, from that single sensor, is necessarily limited, but it isn't zero. The dark sky, even within its limited bandwidth, tells us the universe has a finite age and is expanding. That's a remarkable amount of information to extract from a single channel alone. There's a deeper observation worth holding gently here. Every instrument astronomers have built, sensitive to a new wavelength band or a new kind of signal, has revealed sources no previous instrument could ever detect. The first radio telescopes, in the early 20th century, discovered an entire population of radio galaxies and pulsars that optical astronomy had never even noticed. The first X-ray observatories revealed that black holes accreting matter could be among the brightest sources in the sky within that band, while remaining almost invisible in visible light. The first infrared observatories revealed that a large fraction of star formation across the universe happens inside dust-shrouded regions, completely hidden from optical view. Each new sensitivity has expanded the catalogue of known cosmic phenomena, and this pattern hasn't stopped. Each new generation of instruments discovers populations of sources its predecessors simply couldn't see. The James Webb Space Telescope, sensitive to infrared, has been finding galaxies at extremely high redshifts that were entirely invisible to earlier optical instruments. Gravitational wave detectors, sensitive to ripples in space-time from merging black holes, have registered events completely invisible to any electromagnetic instrument whatsoever. The universe seems patient with us, in a manner of speaking. It doesn't advertise everything at once. It simply waits for us to build a receiver capable of hearing each new channel, and then it speaks through that channel as soon as we're finally listening. Putting all of this together, the universe is far from dark. It glows across every channel we've learned to listen on. The optical darkness of the night sky is a feature of our biology, not of the cosmos itself. With wider eyes, we would see a universe filled with light at every wavelength, structured by sources of every kind, signaling through every available channel. This raises a quiet thought. The dark sky we see in the visible band isn't the universe's full report on itself. It's the universe, filtered through a particular kind of observer with a particular kind of senses. A different observer, with differently tuned senses, would see an entirely different universe. The cosmos itself is far richer than what any single sensor can ever detect. Each new instrument we build, sensitive to a new wavelength or a new kind of signal, simply reveals more of what was always there, quietly, the whole time. There's something genuinely beautiful in that. The universe doesn't advertise itself only in the wavelengths we happen to see. It advertises itself through every channel at once. We're simply too narrow, biologically, to receive most of those advertisements directly. With instruments, we widen our reach, and the cosmos rewards that effort by revealing more and more of its structure. And yet the dark optical sky we see with our own eyes isn't nothing. It's the channel we live in, the one our biology evolved to use. It's the window onto the universe our species has been looking through for as long as humans have looked up at all. The questions it has prompted, including the one we've spent this entire journey working through, have led directly to the discovery of cosmic expansion, the finite age of the universe, the existence of the cosmic microwave background, and many other deep truths besides. The narrowness of our biological window has not prevented us from finding the broader truth. The dark optical sky, properly understood, has been one of our great teachers. So let's step back now, gently, and look at what the dark sky teaches us as a whole. We won't add new facts. We'll simply let the picture settle. We've come a long way tonight. We began with a simple question. Why is the night sky dark when the universe is full of stars? We followed that question through atmospheric scattering, through photographic exposure, through the formal statement of the geometric paradox, through the failed historical resolutions, through the modern resolution involving the finite age and expansion of the universe, and through the rich population of sources visible in wavelengths beyond the optical. We've ended somewhere the simple question never suggested at the outset. The dark sky, properly understood, isn't an absence at all. It's a record. It's a measurement. It's the universe quietly telling us about its largest scale features. Let's gather the threads gently, one at a time. The first thread is local. Earth's daytime sky is bright because the atmosphere scatters sunlight, redistributing the direct beam across the entire dome of the sky. The scattering depends on the size of atmospheric molecules and the wavelength of light, producing the characteristic blue of daytime and the redder tones of sunrise and sunset. Without an atmosphere, even a sunlit world would carry a black sky. The moon shows us this directly. Other worlds, with different atmospheres, show variations on the same theme. A bright daytime sky is a property of having an atmosphere, not a property of the surrounding universe. The second thread is photographic. Many of our space images show featureless black backgrounds behind bright foreground objects, not because the universe is empty, but because the exposure required to image a bright foreground is too short to capture much dimmer background stars. Long exposure images, pointed at empty patches of sky, reveal a universe densely populated with galaxies and stars in every direction. The black backgrounds in planetary images are an artifact of exposure choice, not a description of cosmic emptiness. The third thread is cosmological. The dark night sky we see from Earth, even under ideal conditions and with sensitive instruments, isn't nearly as bright as a simple geometric argument predicts. The universe holds an enormous number of stars in every direction, and the geometry of lines of sight through an infinite stellar universe predicts a sky as bright as a stellar surface everywhere. The fact that the sky is dark instead is evidence about the structure of the universe itself. The fourth thread is temporal. The universe is not eternal. It has a finite age. Light from regions beyond a certain distance hasn't had time to reach us yet. The observable universe is finite, bounded by the speed of light and the age of the cosmos. Lines of sight extending beyond the observable horizon don't terminate on stars at all. They terminate on the universe's own early state, before stars ever existed. The simple geometric argument fails because it assumed contributions from arbitrarily distant stars whose light simply hasn't had time to arrive. The fifth thread is spatial. Space itself is expanding. Light traveling across the expanding universe stretches, its wavelength growing longer over the journey. By the time light from very distant sources arrives, it has often been shifted entirely out of the visible band into infrared, microwave, or longer wavelengths. Still, the optical brightness of the sky is further diminished by this redshift, On top of being limited by the universe's finite age, distant sources still send their light. The light has simply become invisible to optical detectors by the time it arrives. The sixth thread is dynamic. The expansion is accelerating. Some sources now recede from us so quickly that light leaving them today will never reach us. A cosmic event horizon exists, beyond which the universe is permanently out of reach. The dark sky, in its deepest sense, contains directions whose contents will never become visible to any observer here, ever. The seventh thread is biological. Even the universe we can see contains far more light than reaches our eyes. Across the full electromagnetic spectrum, the universe glows in every direction, in the cosmic microwave background, in infrared with dust clouds and cool stars, in radio with pulsars and active galaxies, in X-rays and gamma rays with the most violent sources known. The optical darkness of the night sky is a feature of our biological window, which sees only a narrow slice of the full spectrum. A different observer, with different senses, would see a different sky entirely. These seven threads, woven together, make the dark night sky we see. The dark isn't a single feature. It's the result of many features working together. The geometry of our atmosphere, the limitations of our cameras, the structure of cosmic expansion, the finite age of the universe, the existence of horizons, the mortality of stars, and the narrowness of our biological window onto the spectrum. Each thread contributes its share. Each is necessary to produce the sky we actually see. This is, in its own way, a satisfying answer. It doesn't feel like a single clever trick. It feels like the natural result of how the universe actually works. The dark sky is exactly what such a universe produces. And our universe, by every measurement, is precisely such a universe. The dark sky and the modern picture of cosmology fit together cleanly. Neither needs patching to remain consistent with the other. There's one more observation worth making. The dark night sky has been a teacher. The question of why the sky is dark has, over centuries, driven thinkers to consider the structure of the cosmos at the largest possible scales. It has helped identify the finite age of the universe, the expansion of space, the redshift of distant sources, and the existence of horizons. A puzzle that seemed at first like a small geometric curiosity ended up leading to some of the deepest insights in all of cosmology. This pattern recurs often in science. Small questions, taken seriously, tend to lead to large answers. The night sky, simply by being dark, has told us things about the universe we could not have learned any other way. The dark sky is evidence freely available to anyone willing to step outside and look up. It requires no telescope, no detector, no lengthy calculation. It only requires someone noticing the dark and asking why it's there. Many people, across many centuries, have noticed and asked. Their accumulated answers have brought us to the modern picture. That picture isn't yet complete. There are still pieces to fill in, especially around dark matter, dark energy, and the deep early universe. But the picture is consistent, well supported by evidence from many independent directions, and far richer than the simple, infinite, eternal, static universe of the original geometric argument. The dark sky pointed the way. Generations of careful work filled in the rest. There's a final thought worth leaving with. The dark between the stars isn't empty. It's filled with light we cannot see directly, with light that's been stretched out of our view, with light that hasn't yet had time to arrive, and with light that may never arrive at all. It's filled with the history of the universe, encoded in the photons that do arrive, and in the silence of those that don't. Every patch of darkness overhead carries its own story. Some patches are dark because no star happens to lie along that direction within the observable horizon. Some are dark because expansion has carried any potential source out of our visible band. Some are dark because the line of sight passes through a region of the early universe, before stars ever existed. Some are dark simply because our eyes don't detect the light that's already there. All of these reasons, together, make the night sky we see. None of them is a flaw or a failure. Each is simply a piece of how the universe actually works. The dark is one of the most honest things we're ever shown when we look up. It doesn't pretend to be empty. It's full of a story we're still learning to read. There's a quiet symmetry to how this resolution finally arrived. For many centuries, the question of why the night sky is dark was treated as a puzzle to be solved by adding extra features onto the existing picture of the cosmos. Each proposed feature failed in turn, and the puzzle persisted. Then, in the early decades of the 20th century, the picture of the cosmos itself changed entirely. The universe turned out to have a beginning, to be expanding, to carry horizons beyond which we cannot see. Once those features were properly in place, the dark sky stopped being a puzzle and simply became a natural consequence. The question dissolved, not because someone found the right small adjustment to the old picture, but because the picture itself was replaced by a more accurate one. The dark sky was always evidence about the larger structure of the universe. We simply hadn't yet built the framework in which that evidence made any sense. This pattern recurs across science more broadly, a long-standing puzzle, resistant to every small fix. Sometimes turns out to be evidence pointing toward a deeper feature of how the world actually works. The fix, when it finally arrives, isn't a clever patch on the existing picture. It's an entirely new picture that resolves the puzzle naturally, almost effortlessly, once it's in place. The dark sky belongs squarely in this category. It's one of the cleanest examples in all of physics, of a small visible feature carrying information about the largest, most invisible structure imaginable. There's something humbling in that, and something quietly hopeful too. The universe shows us its features in the gaps as readily as in the lights. The dark sky overhead is a kind of signature, written in absence rather than presence, of how the cosmos is arranged, at scales we can never directly visit. We don't need to travel to the cosmic horizon to know it's there. The horizon makes itself known through the darkness it leaves at the very edge of our line of sight. We don't need to ride along on a photon to know that space is expanding. The expansion makes itself known through the stretching of light over its long journey. We don't need to wait for the universe to age in order to detect that it has an age at all. The age makes itself known in the very darkness of the spaces between the stars overhead. These quiet self-revelations of the cosmos rank among the deepest gifts that careful looking can offer. The night sky is one of the gentlest of them. It's freely available, asks for no instrument, and rewards patient attention with information that took generations of brilliant minds to fully extract. Step outside tonight, let your eyes adapt to the dark, and look up. You'll be looking directly at evidence about the structure of the universe, on scales of billions of light. The dark sky overhead is a quiet teacher. There's a kindness in that. The question of why the sky is dark turns out to have an answer that isn't frightening, isn't paradoxical, isn't adversarial in any way. It's an answer about scale, and time, and biology. It's an answer that lets the universe simply be what it is. The dark sky isn't hiding anything from us. It's showing us, plainly, what a young, expanding, structured universe looks like from the inside, viewed through the narrow window of human eyes. So the next time you step outside on a clear, dark night and look up, and see the familiar stars scattered across the familiar dark, you can carry all of this with you. The dark isn't what it first appears to be. It's full of cosmic history. The stars are the bright parts of a much larger picture. The dark between them is the rest of that picture, painted in colors our eyes were never built to perceive. And the picture, once fully assembled, is one of the most remarkable things we've ever managed to learn about our universe. The sky overhead, dark as it appears, has been quietly telling us about the cosmos for as long as anyone has cared to listen. It tells us the universe is finite in age. It tells us space is expanding. It tells us horizons exist, beyond which we simply cannot see. It tells us the cosmos blazes with light in wavelengths beyond our reach. And ultimately, it tells us there is far more universe out there than there are eyes to see it. So the dark sky overhead, which once seemed like an empty backdrop or an unsolved puzzle, becomes instead a quiet companion to the night. It carries the history of cosmic expansion in every patch of black between the stars. It carries the finite age of the universe in the directions where light hasn't yet arrived. It carries the existence of horizons in the regions that will remain forever beyond our reach. And it carries the narrowness of our own biological window in every wavelength of invisible light flowing silently past us, unseen. There's no urgency in any of this. The dark sky was here long before us, and it will remain long after, doing exactly what it does, telling its quiet truth to anyone who simply looks. The question of why it's dark has, more or less, been answered within the modern picture of cosmology. The answer is gentle, consistent, and quietly satisfying. It asks nothing of you except to understand it, and understanding it requires nothing more than the careful, patient, generations-long work of looking up and asking what's actually there. So let's let the question rest exactly where it belongs, not in worry, but in wonder. The dark isn't empty. It's only young and very far away and shifted into wavelengths your eyes were never built to see. Let your breathing slow. Let the day fade away. Sleep well.